All right, so what we're going to look at today is we're going to look at the idea of conservation of energy. Okay, so how can energy be conserved? Conservation of energy, right? So, how did these things relate? What we talked about last time was we talked about kinetic and potential energy. And so, how do those two things relate to one another? And you've learned this in the past. We're just going to put a little bit of math to it, all right? So, if we think about this, when the bow and arrow is stretched, it gains potential energy, right? It's elastic potential energy, but it's still potential energy, right? And then when we let go, that arrow shoots off, right? And it gains kinetic energy. So how can we know how much kinetic energy it's going to gain? Well, let's think about this. If we just pulled the bow here, right, the arrow might shoot off this way at 10 miles per hour, right? But what happens when we pull the arrow back a little bit farther, right? What if we pull it back here? Well, now what we kind of know is that it's going to go a little bit faster, right? Maybe the arrow goes at 15 miles per hour. And if we pull it all the way back where he had it, right, then we actually have the bow and arrow or the arrow shoot off at maybe 25 miles per hour. Okay. So what we can see is that the greater the potential energy, the greater that I pulled it back, the faster that that arrow went. And so we see the more potential means more kinetic. All right. So we have this because energy is conserved, right? There's this conservation of energy, and that energy cannot be be created or destroyed. Rather, energy is converted from one form to another. And that's what we're going to look at today. And we're going to put a little bit of math behind the kinetic and the potential, right? So think about these energy transformations, right? When we eat food, the food that we eat is converted into energy for us to use to create motion, right? For us to move. When we move, we have kinetic energy, and we are able to have that kinetic energy because of the food that we ate. When we fill up our car with gas, we take chemical potential energy and convert it into the motion of the car, which is kinetic energy. We have energy that's produced from the sun due to nuclear reactions, right? And that energy released in that nuclear reaction is then used by the tree to grow, or any plant to grow. And then when we plug things in, right, we have electrical potential energy, which then is converted into thermal energy, which then heats up our bread and produces toast, right? So that we're not creating heat from nothing, we're using electrical energy to create the heat. So we're converting it, not creating it. Okay, so how can that apply then to what we're looking at, right? So the main thing that we're going to look at is this idea of mechanical energy, right? Mechanical energy is basically the sum of potential and kinetic, right? And the idea is that mechanical energy cannot change for us right now. When you get into higher science, it might, right? But for us, we're going to say mechanical energy is not going to change. Instead, the kinetic and potential energy will change, but the sum of them, the total, the mechanical energy, will not, right? So if we think about here, down here, we have all kinetic, right? As the ball goes up, we're losing kinetic, it's slowing down, and we're gaining potential. And then as we go back down, so up here we have all potential, right? And then as we go back down, we're gaining kinetic. Okay, we're losing potential and we're gaining kinetic, right? So what we're going to do is we're going to do this equation here. Mechanical energy equals potential energy plus kinetic, right? The main thing is that this does not change. Okay? Think about when we did the energy skate park, right? Mechanical energy is the whole pie, right? It's the whole pie. It always is the same. But potential and kinetic are the pieces. So maybe potential is red, right? And kinetic is blue, right? So when we looked at this scenario here, right? Let's do the pie for this. The ball at these three positions, okay? We'll have this be position 1, we'll have this be position 2, we'll have this be position 3, right? Well, at the very beginning, it's all kinetic. So the pie itself is all mechanical, but what makes up that mechanical is all kinetic. At the very top, it's all potential. There's no kinetic. Well, then here at number 3, it's pretty high, so it's mostly potential, but then there's also kinetic. So you notice the pi itself, the green doesn't change. The mechanical energy is the same, but the potential and the kinetic is the thing that is changing. Okay, so if we have a diver, right, and they jump off, they have all potential to start with. And then what we notice is their potential goes down as they get lower and lower. Whereas their kinetic energy instead goes up. It starts at 0, then 3, then 5, then 7, then 10. So the kinetic energy is increasing, the potential energy is decreasing, but the mechanical, which is the combination of those, is always 10. Right? So those two added together still give me 10. Okay? So we can use that when we're doing some more complicated questions, right? So think about this. The mass of a roller coaster with everyone in it is 1,000. You are clocked at 50.5 meters per second at the bottom. What's your kinetic energy at the bottom of the hill? So let's do that calculation. At the bottom of the hill, we have kinetic energy. We calculate that using 1/2 mv squared, right? That's 1/2 times 1,000 times 50.5 squared. That gives you, let's plug it into our handy dandy calculator, 1/2 times 1,000 times 50.5 squared gives me 128. I'm going to round my last zeros. So that gives me 1,280,000 joules. Okay, well that's down here. Again, here's the idea. Here's my pi down at the bottom. Here's my pi down up at the top. Here's my pi in the middle, right? At the bottom, I have all kinetic. At the top, I have all potential. And in the middle, I have half. And I apologize. I think I swapped the colors here, but whoopsie. I think we get the idea, right? It's half and half. Okay, so what I can then ask is, what's the potential energy at the top? Well, I don't have to do any calculations. I've already done it. Because what I know is that the potential energy stays the mechanical energy stays the same, right? So the mechanical energy at the bottom, 1,280 or 1,280,000. Mechanical energy in the middle, 1,280,000. Mechanical energy at the top, 1,280,000. There's no potential at the top or no kinetic at the top, so it's all potential. All right, last example here. I'm sorry, I'm trying to go fast because I know there's a lot of math to this, but here's the idea. We're going to look at this situation, and what we're going to do is we're going to try and find mechanical, potential, and kinetic velocity height depending on the situation. What we're going to say here, right here, we're going to say that the velocity is 0. We'll say that this is as maximum height that that person can get to, so we'll say that is 0. Okay, so what I'm going to do is I'm going to color coordinate this. Everything I do for the first position I'm going to do in red, and all the information I know from the first position I'm going to then write in red. So we know the mass of the rider is 60 kilograms. We know they're going at 8 meters per second. We know our height here at the very beginning is 0. They're on the ground. So what we know is the potential energy at the very beginning is 0. Okay. What we can then calculate is my kinetic energy. That's 1/2 mv squared. And that's equal to 1/2, touching the iPad here, times 60 times 8 squared. Don't forget the squared, right? It's the main thing that people forget. So this is 30 times 64, which is 1,920 joules. So that's my kinetic energy, 1,920. So what I know then is my mechanical energy is 1,920 because it's the combination of potential and kinetic. Now what I can then do is say my mechanical energy here is 1,920. I can say my mechanical energy at the very top is 1,920 because that doesn't change, it stays the same. Okay, great. Let's go to position number 2. We'll do that in green. Position number 2. We have a height here. And because I have a height, I can find a potential energy. MGH. 60 times 10, that's my gravity, times my height, which is 1. 60 times 10 is 600, times 1 is 600. So my potential energy is 600. Okay. Then what I know right away, because I know potential and kinetic equals mechanical, is I know that this is 1,320, right? Because 600 plus 1,320 equals 1,920, right? So it's my potential plus kinetic gives me my mechanical. Okay. I can then calculate my velocity. And I'm going to do that by saying kinetic energy equals 1/2 mv squared, which my mechanical or my kinetic is 1,320 equals 1/2 times my mass, which is 60, times velocity squared. Right? So I'm going to 1,320 equals 30 v squared. I'm going to divide each side by 30. 30 goes away there. I get 1,320 divided by 30, which is 44, equals v squared. Then I need to square root because I want v, not v squared. If I square root that value, I get 6.6. So he's going 6.6 meters per second, which makes sense because if we look at the beginning, he was going 8 meters per second. He's gone higher. He should slow down. 6.6 makes sense. Down at the very top, he's going 0, right? So what I can know then is I can know that my potential energy, my kinetic energy is 0. He's not going anywhere. He doesn't have a velocity, so his kinetic energy is 0, which then tells me the potential energy is 1,920 because that plus 0 has to equal my mechanical, 1,920. And then I can find the height, right? And so for position 3, the only really major calculation is finding the height. That's potential energy equals mgh. So that's 1,920 equals 60. I'm running out of room here. Let me rewrite this, guys. Sorry. Okay. Potential energy equals mgh. 1,920 equals 60 times 10 times h. This is 1,920 equals 600. H. Divide each side by 600. 600 goes away here. And I get my h equal to 1,920 divided by 600. 3.2. Which makes sense because it should be higher than 1. Right? And so that's how I can use that to show velocity, height, any of those calculations dealing with kinetic and potential based on how the energy is conserved. Right? Hope that makes sense. Let me know if you have any questions. Sorry, it's a little bit longer. It's a little bit more calculations, but just showing how kinetic and potential all go together.